Welcome you all to this course on electron diffraction and imaging. Today's class we will devote to the basic principles of transmission electron microscope, a brief introduction, and this forms the basis of all other lectures which goes into details into how we get images and diffraction patterns, various modes in which we can operate the microscope. Okay. The first question which arises when we talk about a microscope is that why do we require these tools? That is the first question. The answer to that is that we wanted to observe features beyond the resolution limit of our eye. Okay. That means that many features we are not able to see, like if some small speck of a broken glass or a thorn is lying, we are not able to see it. Why is it so? That means that what is the resolution of the eye? That is the question which arises. The resolution of the eye is around 0.1 to 0.2 millimeter. Okay. Then now what we need is that we require equipment which can magnify to a large extent. But what it happens in reality? Reality essentially is that when we beam, whether it is a light radiation like when this falls onto this wall, okay, this phenomena occurs at some resolution which is dictated by the nature of the radiation and the nature of that sample. But and the signal which is coming to our eye is also coming with that resolution, but we are not able to see it because our eye does not have that resolution. So, if we can magnify those features so that they are well separated for eye to be resolved, then we can see that. That is what it dictates what is a magnification which is required. That is what the job which all these equipments do. Okay. The dictation of resolution, that is what determines the resolution, is essentially the capability of the equipment and the probe sample interaction. But finally, we have to look with our eye and analyze the result, for which it has to be magnified to that extent. That is what all the lenses do that job. Okay. What is the plan of this lecture? First I will give a schematic of a microscope, then what are the various components which are there in the microscope. Then I will talk about the specimen probe interaction because that forms the core of the microscopy study. Then different types of microscopes which are formed, transmission electron, based on this interaction, the classification I will give. Then we will talk about the lenses and ray diagrams, how the different rays gives rise to different type of images and magnification, which we will talk about. Then another thing which is important for any microscope or anything is that resolution, magnification, and finally when we have to see it, a contrast has to be there, otherwise we will not be able to see any features, that we will talk about. Then another aspect of it when we use any lens system is what is called as a depth of focus and depth of field. This is very important, this aspect we will talk about. Then the last one is the different modes of diffraction and imaging. With this brief introduction to electron microscopy I will cover. Okay. What are microstructural characterization tools as such we have? We have eye itself is having a lens and a retina which is like a CCD camera. So, that itself acts as a to some extent it may be magnifying, depending upon the position it can demagnify. Essentially what happens is that eye is also like a magnifying lens. Then we can have a magnifying glass, we have optical microscopes, scanning electron microscopes, then we have field ion microscopes, atom probe, atomic force microscopy, scanning tunneling microscopy, atom probe microscopy, okay. Then transmission electron microscopy. Generally many of these techniques are called as surface techniques, and transmission electron microscopy is called as bulk technique, but attaching tomography technique to many of these equipments, we can make them also into a bulk characterization tool. Okay. But most of the characterization tools are combination of these various types of phenomena which occur, and that is how that equipments are made depending upon the convenience and what all information we frequently require. On that basis it is being done. At this juncture, I should just mention that there are two types of microscopes are there, or two types of equipments I should say, which reveal the characteristics of the sample, microstructural characteristics. One is using lens, another is without any lens. Okay. The ones which do not use any lens are atom probe, okay, and scanning tunneling microscopy, then atomic force microscopy. They can give any sort of a magnification. I will not go into any of these details, but one should be aware of it that these also magnify that objects, okay, but they do not use any lens. Okay. That will form a separate lecture later. But in a microscope, like whether it is an optical microscope or a scanning electron microscope or a transmission electron microscope, you have some lenses. So, some lens aberrations are associated with it. So, we will talk about, that is why I said that we should know about lenses and resolution, lens aberrations, magnification, all these things come to the picture. Okay. If you look at a schematic of any microscope which is to be constructed, what all things which we require? One, first a probe of radiation has to be there. Okay. That probe of radiation falls on that sample surface. Quite often the radiation which comes from the probe, okay, like for example, if it is a source from which the radiation is coming, it may be emitted in all these directions. Okay. It can so happen that there can be a variation in that intensity of the beam. So, we require some illumination system which makes that beam fall on that sample, okay, and this system we call it as the condenser lens system, correct. So, what does condenser lens system do? Essentially it makes the beam uniform. So, if the beam is uniform, then what is the difference which comes from place to place? Okay. That is what the contrast, and that shows how the beam has interacted with the sample at different regions, and we can do a quantification only if we make sure that the beam which falls on the sample is uniform, correct. That is what the condenser lens does that job. Then comes the specimen, the sample itself. Okay. Depending upon the microscope, we should have different type of samples, which we will talk about it as we progress through the lecture. What are the specifications which is required, okay, for the specimen to be examined in a TEM. Then comes the objective lens, is the one which the beam which passes through the sample and comes. Okay. Now, the real part of the microscopy comes. Okay. Objective lens essentially gives a magnified view of the object. Okay. It acts like a magnifying lens, and then what we have is that a few more lenses are there, because the type of magnification which we go, one lens cannot give this sort of a magnification. So, many more lenses will be required. Okay. Then there is a projector lens which projects it onto the screen. Then we have a camera, because finally we have to record this. Okay. We require a recording device. It could be a camera, okay, with a photographic film, or it could be a CCD camera. There are various types which we can have. Okay. First, let us look at a schematic diagram of an optical microscope. Okay. Whatever I have explained, exactly that same thing which we look at it, because everybody is familiar with optical microscope, or you people have some idea of the what are the basic components which are there in an optical microscope. We have a light source, okay, and then there is an aperture, then there is a condenser lens system. Then in a transmission mode of an optical microscope, it falls onto a sample, that is this will be falling onto a sample here, okay, and then when it comes out we have an objective lens, okay. Then we have a projector lens which projects it onto the screen. Okay. In an actual microscope, it is like a schematic of a transmission electron microscope is shown in this diagram. Okay. In a transmission electron microscope, instead of a light, we use essentially a electron beam as the source. Okay. And in a normal microscope, what we do is that the light source, generally we use a monochromatic beam, and the beam has to be highly coherent. Okay. Here also the beam has to be monochromatic, for which some voltages have to be applied to the electrons which are emitted from the source. Okay. So we can have a requisite wavelength. This we will come later. Okay. Then we have a condenser lens system. Generally in a transmission electron microscope, 2 or 3 condenser lenses are there. If you look at this diagram, here it is being shown with some crosses. This is because these are all magnetic lenses, which I will show later schematically how it resembles in principle like a convex lens. Okay. Then we have a objective lens, then we have some few projector, few intermediate lenses are there, okay, 2 or 3, and then we have a projector lens which projects this onto the screen. Then we can have a camera here or a CCD camera, okay, with which we can record it. This is just a photograph of a conventional transmission electron microscope, how it looks like. Okay. In this microscope, this is the gun part. We have condenser lenses which are there here. Okay. Then we have this is where the sample is introduced, objective. You cannot see any of these things. Okay. This is a microscope which is essentially a remote controlled one, so that you do not see a screen also. These details about latest developments I will go into it later, but not in this class. Okay. Let us first now look at the illumination system before the specimen, what it happens. Okay. The first thing we should have is a electron gun, okay, which is the source of electrons. Okay. As you look at this diagram, okay, it's in this case it's a thermionic, it could be an emission where a filament is heated to a high temperature, so it emits electron, and then we apply some voltage, okay, to control the beam current, and in that process application of the voltage, this acts like a lens and focuses it onto a point. This point is called as the crossover, and the size of this and how much is the beam current which is going to be there, that decides the characteristics. Okay. This will come shortly. Then we have condenser lenses are there, which are used to make the beam either parallel or convergent or divergent, but uniform on the sample surface. This is only just a schematic of the ray diagram. Okay. And another important thing is that in an optical microscope we use lenses, but if you use a glass lens problem associated with this, they come with fixed focal length. So we can't change the focal length of the lens. So if 2 lenses we use, if you want different magnification, suppose one lens is kept here with respect to an object, okay, and another lens is kept here, then we may get some magnification of that image. But suppose we want higher magnification, we may have to move the positions of these lenses to get higher magnification, okay, or choose lenses which have different focal length. These are all the 2 options which we have. Whereas in a since the lenses are electromagnetic lenses, just by changing the current which is applied to the lens, okay, we can totally change the focal length of the lens. That is the advantage in an electron magnet. We do not have to change the position of the lens, you just change the current, all the focal lengths are changed. Okay. Then as I mentioned, parallel, convergent or divergent beam we can obtain. Okay. Now we will talk about the source of radiation. In the case of a transmission electron microscope, the source of radiation is essentially electrons. As we know, electrons are particles, but we know from de Broglie's concept, okay, with every particle which is moving, we can associate a wavelength with it. It can be considered as a wave as well. Okay. This wave concept is very much necessary because all the explanations or quantification, the theoretical development of electron microscope is all based on this wave concept. Okay. And the wavelength of the radiation lambda is essentially given by h, the Planck's constant, divided by p, the momentum. Okay. Then the p depends upon m, the rest mass, into velocity. Okay. This, if we apply a particular voltage, okay, to accelerate it, then we know that if a voltage is applied, okay, then we can equate half mv squared. Okay. This will be into E into V, it's the voltage applied, E is the charge, that's also in terms of energy. From this we can find out what the velocity and substitute and get formula for the non-relativistic correction which is given here. Okay. But we know that electron mass is very small, okay. Even for 100 kV if we apply it, the speed with which the electron travels is very fast. So, we have to take the relativistic correction into account. When we do that, this is the sort of a formula which we get it. Okay. This which you might have studied in physics or relativistic theory, all other topics one might have studied. Okay. Essentially, in this particular slide, I will talk about, so far what we talked about, how to find out given a particular voltage, okay, to the electrons, what is the wavelength which is associated with it. And as I mentioned that there are many types of electron sources are there. The sources are, one, we can have a tungsten filament and just heat it, okay, to very, so electrons will be emitted by thermionic emission and these electrons can be accelerated. Or lanthanum hexaboride, that also by applying a voltage and heating it to a temperature, and the temperature is around 1700 K. Then another is that even without raising the temperature, if you take a very fine tip, okay, apply a voltage to it, the field lines, that is generally what happens is that if a tip is there like this, a tungsten, if we apply field like this, if the electric field closer to the tip is very high, then it could extract electrons from that sample. That is what is done in a field emission gun. Okay. One is a cold emission gun, field emission gun, that is the best, but it has lot of associated problems and technology which is required. Maintaining, more than the technology is available, maintaining it is going to be difficult. If you wanted to use an equipment routinely, we would like to have a system which is very reliable and breakdown is less. For that, the Schottky field emission gun is there, where it is heated to a slightly higher temperature, so that emission of that electron becomes much faster. What is essentially important is that if we look at the current density, okay, it is about something like 5 for tungsten, and if you take the number, it is about something like 20 times more. Here it is about compared to LAB6, the Schottky is around something like another 1000 times more, and compared to Schottky another 10 times more is the cold FEG. Okay. But crossover, if we see where is that beam, that decides what is going to be the current density. For many applications, the current density is important. Here the crossover is quite large, 10 to the power of 5 nanometer or more, whereas it is 10 to the power of 4 for LAB6. Here it is only 15 nanometer. You can see the order of size. Here it is 3 nanometer. That means that if the beam, all the beam, very high intense beam, that means that is what we call it as the brightness of the beam. If the beam comes from a point and if it is monochromatic, then it satisfies all the condition for diffraction or interference, you can say that. That means that the beam is monochromatic and the beam is highly coherent and it has got both spatial as well as temporal coherence. Okay. This sort of and then another is that for many applications we have to look for what is the energy spread. That energy spread, if we look for, in the case of Schottky and cold emission gun, that energy spread is less. Why do the energy spread is important? It should be less energy spread because the chromatic aberration depends upon that. The simplest which we can think of at this stage. Okay. And since it is electron source, we require a vacuum. Okay. That vacuum which is for a cold emission gun, if you look at it, it is around 10 to the power of minus 9. Whereas with 10 to the power of minus 6, minus 7, Schottky field emission gun could be maintained. Okay. Others the requirement are less, but about the vacuum system we will talk towards that end of the this lecture. Okay. And the filament lifetime also, if you look at it, this is about 5000 hours lifetime for the Schottky detectors. Nowadays most of the microscopes are coming with essentially field emission guns, the Schottky field emission gun. Okay. Then so far we have talked about the gun, okay. The condenser lens system I had just shown also that two types of two lenses are used, or sometimes three lenses are there to make an uniform beam fall on the sample surface. But when that electron beam falls onto the sample surface, okay, the type of information which we require is what is most important to construct a microscope. So, let us look at what is the type of beam interaction. If the primary beam is falling onto the sample, okay, the primary beam itself could be scattered from the sample itself, correct. That is what we call it as the backscatter. That will also happen. That is what is used in scanning electron microscopy. Then from the sample some secondary electrons could be emitted. These secondary electrons could be just electrons with very low energy, or like Auger electrons or X-ray photoelectrons, they are also secondary electrons. These are all the various signals which come out from the sample. These are going to phenomena, it will be covered in a later class. At this juncture you should know that these are all the types of signals which come, and X-rays characteristic of the sample will also be emitted. Okay. Suppose the sample is and then the current, the beam which is absorbed, that is a specimen current, that also can be used as a signal. Other than that, if the sample is thin, the electron beam will pass through the sample or come out through the sample, interacting with the atoms which are going to be there. Here during this interaction the electrons are reflected back, here through the interaction the electrons are travelling in the forward direction. So, in this direction there are electrons which are coming, transmitted electrons, which might have been elastically scattered, they have not lost an energy, that is one type of an electron. Some electrons can interact with it and lose some energy, okay, and then the beam energy might have reduced by some particular amount. These electrons are called as inelastically scattered electrons. These inelastically scattered electrons, okay, could be used as in a technique which is called energy loss spectroscopy. That also gives information about the type of atoms which are there. So, chemical composition information we can get it. And when the primary beam has lost some energy, what is the another thing which happens? Okay. This energy loss means that it has excited the atom from one state to another state, okay. K level to an L level, it is removed an atom from to a vacuum level. Then when a vacancy is created, an electron from an L level can come down to fill the vacancy. That is what it comes out in as the characteristic X-rays. So, these characteristic X-rays also gives information about the elements which are present on that sample surface. Okay. These are all the information which we can get it from the microscope. And another important thing which we should remember is that since it is an electron beam, we use it. Electron beam can be focused to a point so that we can make the beam fall at one particular point, or it can be made to fall over a larger region. Okay. So, the various modes in which we can design a microscope depending upon whether it falls on a region and whether it falls on a specific point, okay, which is determined by the beam size. Okay. We can have different types of microscope. That is why how another microscope which has come, which is called as a scanning transmission electron microscope or STEM. Okay. Now, let us look at what are these type of microscopes which we can have. The earlier microscopes which were made are called conventional transmission electron microscopes, where the beam passes through the sample, the transmitted electrons which are coming out, which are elastically scattered, they are used to form images and look at diffraction and imaging mode, that is one. Now, with the availability of various detectors which can be incorporated into the microscope column, now we can use inelastically scattered electrons and X-rays also to get some image information. These microscopes are called as analytical electron microscopes. That is one class of microscope which is available. Then another is that depending upon the resolution of the microscope, if the resolution is smaller than the atomic the spacing between atoms in the sample, okay, it is about less than 1 angstrom, then we will be able to resolve atoms on the sample, that is how an image should come. So, this is called as a high resolution transmission electron microscope. Okay. Then the other is scanning transmission electron microscope, which I mentioned, that is if we can make the beam, focus the beam onto a very fine point, okay, and then scan the beam on the sample surface, and the signal which comes out we collect it, okay, and use that to form an image. Then we can this mode of operation is called as scanning transmission electron microscope. In the present day microscope with FEG detector, we can make the beam as 0.1 nanometer, that is almost about 1 Armstrong beam size. That means that there also we can get atomic resolution. Okay. So, these are all the way or the in which the electron beam interacts with matter, and this has opened up the scope having different types of microscopes. Now various microscopes are available with different types of configurations like this, and some of them will evolve, but it is always better to have microscope with each of them, because that is the one which gives the best capability of each technique. Okay. So far I talked about various types of signals which are coming out. Now the question arises is, what is a microstructure? General concept of a microstructure, what we have is that we think that if a light is scattered from a sample and the scattered variation in intensity gives rise to a contrast, that image is what is conventionally we call it as a microstructure. But that is not true. The microstructure is nothing but mapping of a property distribution. Suppose we have a sample, okay, like a nano intender if it is there, okay. We can have a sample and put the nano intender to take indentation on various, look at what is the hardness value and plot it. This is also a microstructure. So, microstructure, if you ask me, the way I will define is mapping of a property distribution in a specimen or a sample is what a microstructure is. That could be done using lenses, which is where we use for scattered beam, okay. Like the way we are in a scanning tunneling microscope, okay, or an atomic force microscope. It is essentially atomic force when we bring a probe close to a, that is also one way in which we get a microstructure. It is essentially we get an atomic resolution microstructure there, right. So, all are microstructures, okay. So, a general definition of a microstructure is nothing but it is a property distribution in a specimen which has been mapped, okay. Now, when the beam has fallen onto the sample, it comes out of the sample surface, okay. We can assume that the beam is initially assumed we have got a parallel beam, okay. That parallel beam when falls onto the sample surface, depending upon the interaction with each of the atoms, beam will be scattered in different directions. So, what can happen? Beam could be scattered from this region in various directions. Similarly, here also, various directions the beams could be scattered, okay. This scattered beam which comes out, beam which has been scattered in various direction is what is falling on the lens, correct. That is what essentially is being shown. We have taken 2 points on the object. From here a beam is scattered in this direction, which is we can say that it is the same direction as the incident beam. So, it is we call it as a transmitted beam, and then these are all the scattered rays, okay. These scattered rays, now let us look at what is the property of a lens, okay. We have studied about the lens in maybe intermediate class, okay. Essentially from the ray optics what we know is that the rays which are parallel to the optic axis, all of them are focused at the back focal plane, correct. And the ray which are all parallel to each other and also close to optic axis, they are also focused to a back focal plane, okay. That is what essentially is being shown in this diagram. The ray which is travelling in this direction, they all get focused from this point, that is, but these rays are emanating from different points on the sample, that is rays emanating from different points of the sample, but parallel to each other, they are focused at some particular point. What is diffraction? Diffraction is nothing but the ray when it is a beam of radiation is falling onto the sample at a particular direction. When we look at it, all the rays which are emitted from different points on that sample, they come together and join. When they come together and join, if they are all in phase, they add together, then we say that a constructive interference and a diffraction peak is occurring. Other regions, that intensities will change. So, this is how you get a diffraction. That means essentially at the back focal plane is what we are getting, especially for a crystalline sample. This we are talking about, but this is true for other material also. But that part of going into the nature of the diffraction and will be covered in a diffraction separately, not here. So, essentially we get what we get, it is a K-space information or a diffraction information. Okay. K-space because that momentum space is called as a K-space, or this can be called in a sample, if we consider, we call it as a, this can be called as a reciprocal space also. Okay. And then where is an image which is being formed. Okay. So, if you try to define what is a diffraction plane, diffraction plane is the one in which rays which are parallel to each other, okay, but scattered from different points on the sample surface or focused at a point. That plane is called as the back focal plane or the diffraction plane. That is what this plane is. What is an image plane? Image is nothing but a magnified view of the object we consider it, which we are getting it. That means that all the rays which are emitted from this point in all the directions should be brought back to the image plane at a particular point. Then only we will get a true representation of that object. Object has to give a true picture of the image has to give a true picture of the object. That will come only when all the rays which are scattered in different directions from a point, they are brought together. That plane is called as the image plane. Okay. So, that means that if you look at this figure for any lens, okay, it has two planes are there. One plane is a diffraction plane, another is an image plane. So, from the sample, when the scattered beam comes out, it does not matter which the source of that radiation is. If the source is coherent, you get both diffraction and image information from different regions of the sample which you can obtain. This is a property of the lens. Okay. This is how an image plane is defined. And what is magnification? Magnification is distance from object to a lens. Okay. That is distance from image to a lens divided by the distance from object to the lens, that is V by U we traditionally write. That is how we get magnification. Okay. And for a lens, how these V and U are related? These are related to a focal length by this relation 1 by U plus 1 by V equals 1 by F. Okay. So, this defines what is going to be the magnification which we can get. All this information is embedded into this. So, if we kept an object at particular place, at what place we have to that image will form. Okay. Because back focal plane is one which is known from the focal length, that is well defined for the focal length, but the image plane depends upon where we keep the object, correct, and that is given by this relation, and the magnification also will depend upon that. These things you people have studied in 11th and 12th. I am not going into any of these details, I will leave it here. Okay. The rest, because we considered up to an object, objective lens. Okay. From the objective lens, okay, when there is, there is a back focal plane where we have a diffraction, and the image plane we have another type of an image. Okay. It is that image of the object. Here it is the diffraction of the object which we are getting it. Diffraction also contains some information about the object. You can say that both of them are giving information about the object, okay, but in different way. Okay. Now, if we wanted to get the final image, okay, we can use other lenses like many intermediate lenses and projector lens, and we can form that image on the viewing screen. This is only just being shown. In that picture which I had shown about the microscope, I said that 3 intermediate lenses are there and then 1 projector lens to get it. Okay. Generally, okay, when we look at that image, finally first we started with telling that we wanted to see objects or features of an object, okay, which cannot be resolved by the eye. That means that we know in an optical microscope we say that we can resolve up to maybe about 400, 300 nanometers. Okay. What is the resolution which we can have in TEM? We will talk about resolution little bit later. In a conventional TEM is of the order of around 0.2 nanometer. Okay. Features of this size we should be able to resolve. Okay. What is the magnification which we can go in a microscope? The magnification we can go up to 500,000 to 1,000,000, that is 1 million times magnification which we can go. The question comes, why we require this magnification? That is, if we take a resolution, a feature of this resolution, if we wanted to resolve, that means that when we talk about resolution, finally we wanted to see with our eye. That means that 0.1 or 0.2 millimeter is the separation that feature should have. So, this divided by the resolution gives you what is the minimum magnification to which the object should be magnified. More further you magnify it, we can see with our eye without any strain to our eye. Otherwise, the minimum magnification, it will be still straining, but we can see them separate, correct. That is what essentially is being done. And this magnification, when we have to use it, no lens can give you 500,000 magnification, correct. So, we require many lenses, we have to use it. In a microscope, the objective lens normally in an electron microscope gives a magnification of about 50, okay, and the focal lengths generally are of the order of 2 to 3 millimeter. Okay. Objective lens magnification is around 50 times, focal length is around 2 to 3 millimeter. Okay. And what we are thinking of is 500,000 or 10 million. For that, if we use further another 3 intermediate lens and a projector lens, each having a magnification between 10 to 15 times, then we will be able to reach this magnification. Essentially what we do in this is that when we wanted to see a very large magnified view, the microscope size is limited. So, the screen is of a particular size. That means that we choose smaller and smaller region from the sample and magnify it, correct. That is what essentially is happening. It is not that the full sample can be magnified, then we will not be able to see it. So, the area which we will be scanning may be a few nanometers, that will be magnified to a few centimeters. That is how the magnification is done, because the beam has to pass close to the optic axis and then only the aberrations will be minimized. So, that is the limitation, correct. As the magnification increases, only a smaller area is being seen. Okay. Right, this I had mentioned. The projector lens acts like an eyepiece in an optical microscope. Then recording of images, how we can record. This screen is essentially a fluorescent screen which we use it, where as the electron beam hits on this one, lights are emitted, and the intensity of the light radiation depends upon what is the energy with which the beam is, not the energy, it is the number of electrons which are falling on each point, that determines the intensity which is coming from that. And if the variation in intensity is from region to region, then we see that there is a contrast. That is how we are able to see an image. But this is one way of looking at it, but quite often we have to quantify. Then what we have to do? We have to record them. Okay. The recording can be done using either a CCD camera. Okay. I will just mention about CCD camera a little bit, or another technique which is called as an image plates. Okay. Image plate is also looks like a normal film camera in which we can expose it and we can use that, okay, to read using a laser light and convert that into a quantitative signal. Okay. And the advantage between of CCD camera and image plate over film is that in film, when it gets recorded, the intensity variations from region to region is on a logarithmic scale. So, when it gets on a logarithmic scale, to convert it back into a linear scale is difficult, whereas CCD camera and image plates, okay, both it is essentially a linear scale in which the each photon comes, it is counted as 1 like that, or some proportionately. So, it is an linear, it becomes easy to do processing of the signal which has been collected. That is the advantage. In fact, image plates is something which is now being used not only in electron microscopy, it is being used for, if you go to any radiography place where you wanted a chest X-ray or any of these X-rays to be taken, they do not use films now. Okay, it looks like a plate, they put it, take it, expose it, and then they immediately put it to a this one scanner. That scanner immediately scans that, and it is that same image plate which is being used here also. Okay. As I mentioned that so far we have almost covered about the various components of the microscope. Okay. And since electron beam we are using it, okay, we can't use a glass lens, okay, it will be absorbed. So, we have to use a lens which can deflect electrons. Okay. So, we can have either an electrostatic lens or an electromagnetic lens, and in a microscope we use an electromagnetic lens. Okay. Here you look at it in electromagnetic, if this is the direction in which the flux is being applied, okay, all the electron beam which are travelling parallel to this direction, okay, this electron beam will be undeviated. If any electron beam has got a path, okay, which is slightly away from this axis flux line, that will be, okay, a force which will, Lorentz force will be acting on that. Okay. What does this force will do? It will make it go on a circular path. Okay. So, finally what happens is that if there is a particular region over which the field applies, when it is from here, when it enters the electron beam which is deviated, it, since it has a high velocity, it is moving also, and the Lorentz force is acting. So, it takes a helical path and comes back here, and when it comes and joins that optical and the optic axis, when it comes, the beam has actually not only moved along a helical path, this gives rise to a rotation of that image also, that one should remember. This is the expression which we can write it, the force equals E VB sin theta, because this is nothing but sin theta is that theta is nothing but the angle between velocity and B, because it can be written as F equals E into V cross B. Okay. V cross B, if you take the magnitude of it, it is nothing but VB sin theta. It is okay. Okay. So, it will be a helix, and then if you look at the field which we apply 1 Tesla, this radius turns out to be in most of the microscope less than 1 millimeter. That means that the beam is very close to the optic axis. Okay. Then as I mentioned, there is a rotation of that image also is occurring, and how does these electromagnetic lenses are being made? If you take a wire and pass a current through it, we know that perpendicular to this electromagnetic there is magnetic field is generated. Okay. In a microscope what is done is that you make a coil like a solenoid, okay, like this. Okay. This is the direction in which the field will be working applied, and in these two ends if you look at it, okay, the flux lines will be there. So, this will be changing the field lines, changing it like this. That is how it becomes like a look like a lens shape. Okay. Essentially what is happening is that this is what is being shown. These are all essentially the wires which are coming through the plane of this screen. Okay. These are all the copper wires which have been wound around it, so many coils, and pass the current through it. By controlling the current, there are formulas which will come later. On that basis, we can make this work as a lens, correct. So, when it works as a lens, essentially what is going to happen is that then we can cover it with a magnetic one, that is, it is a soft iron. If you put it, that will absorb all the magnetic field. Where an opening is there, that is the only where the field lines leak out of it. Okay. Then this acts like a lens, and from a point where the electrons are traveling in different directions, they are brought back to your focus. So, this is something acts like a lens. Okay. This is essentially how typical lens looks like, and what is important is, as I mentioned, is that we pass a current and that determines the focal length. So, when we apply very large quantity of current, then that can heat the coil also. So, maintaining the then the current will change. So, maintaining that current, the temperature, the coil has to be cooled. That is what essentially is being done in a microscope. And by changing the current, as I mentioned earlier, the focal length can be adjusted. Okay. This is a typical diagram of a lens. Okay. In this, if you look at it, these are all the various that is a coil with a particular number of coils, okay, per unit length which has been chosen. So, that controls the magnetic field, and you can see that the magnetic field here it is like this. In this you see that how the magnetic flux, the field lines change. So, this looks, the shape looks like now that of a convex lens. Okay. And in fact, this acts like a convex lens. In an electromagnetic lens, you can only make a convex lens and you can't make a concave lens. So, whatever the aberrations of the lenses, we can minimize it, but we have to live with it. Okay. Now, we have to talk about the resolution of a microscope. Okay. What we will do is that the resolution, magnification and all these aspects we will cover in the next class. So, what we have covered so far is essentially a simple construction of a microscope. Now, about basic information about resolution, how the lens aberrations modify the resolution, okay. This depth of field, depth of imaging, which is important for a microscope, that we will cover it in. Okay. Then different modes of in which the microscope can be operated, in the diffraction mode or in the image mode. Okay. Then little bit about the vacuum systems and all these things. Okay. Then about some simple information about what all information which you can get it from a microscope. These aspects we will cover in the next class. We will stop here now.